Welcome to the NPTEL course on robotics, basics and advanced concepts. This week we will look at kinematics of parallel robots. Last week we had looked at kinematics of serial robots. Okay, so the contents of these lectures in this week are: first we will have some introduction to parallel robots, then we'll look at the loop closure constraint equations in this first lecture. In the second lecture, we'll look at direct kinematics of parallel manipulators. Third lecture, an important concept in parallel manipulators called mobility. Fourth lecture, we'll look at inverse kinematics of parallel robots. And last, we'll look at this very well-known problem of direct kinematics of Stewart platform manipulators. So as I had mentioned, there will be 5 lectures in this part of kinematics of parallel robots. So let's start. Introduction. So what is a parallel robot? What is the main difference between parallel and serial robots, which we looked at last week? In a parallel robot or a parallel manipulator, there are one or more loops. Okay, so there is no real first or last link. In the serial robot, remember, we had a fixed link and then a link and a joint and a link and a joint all the way to a free end, which was the end effector. In a parallel manipulator, such an arrangement is not there. So as a result, there is no natural choice of end effector or output link. Okay, so we need to choose or say this is my output link. Another consequence of one or more loops is that the number of joints is more than the degree of freedom. Okay, and as a consequence, several joints are not actuated. Remember, for serial robots or for in general Grubler's-Kurzbach criteria, we found that we could find the degree of freedom of any mechanism, and the degree of freedom was same as the number of actuated joints which are possible. So we have several unactuated or passive joints, okay, and in a multi-degree of freedom parallel manipulator. Okay, so hence we can also use multi-degree of freedom joints. So if the joint is passive, we don't need to put in actuators at that place, and hence we can use multi-degree of freedom joints. So you can think of a spherical joint which has 3 degrees of freedom, but we don't need to put 3 motors to implement that 3 degrees of freedom. So hence such a spherical joint was not possible in a serial robot, but in a parallel robot it is possible because it need not be actuated. Similar to serial robots, there are 2 main problems. One is direct kinematics and one is inverse kinematics. Before we go into these problems and look at it in more detail, let's look at some simple parallel robots, examples of parallel robot. So the first is this 4-bar mechanism. This is a planar 4-bar mechanism. It is 1 degree of freedom, okay, and it is very well known. Okay, so many people will not say that this is a parallel robot, but let's just extend our definition of parallel robot to include 1 degree of freedom closed loop mechanisms also. Okay, we will be using this 4-bar mechanism extensively in this week because it is very simple to analyze. We can do all the calculations and derivation of equations by hand, and also we can very easily see what we are getting, whether they make sense or not. So in a 4-bar mechanism, we have a left fixed joint here, which is denoted by OL. Then we have another joint, rotary joint, which is here, which is O2 or second joint. Then we have a third joint and a fourth joint. So this forms a loop. So we start from the fixed end, go to the second joint, go to the third joint, and come back to the fixed base again. Okay, so this is a one single loop, and in this loop we can define a coordinate system L, which is the left x and y axis. The origin is at OL. We can also likewise define a coordinate system R, which is on the right fixed point, and this is XR and YR with the origin OR. And then we have link 1, link 2, link 3. Okay, these are the moving links. Okay, so with link lengths L1, L2 and L3. There is also a fixed link which is of length L0. So that is the distance between the left fixed point and the right fixed point. Okay, so this is a very well-known example. This has been studied by many researchers in both mechanisms and robotics community, and this link 2 is also called the coupler, and typically in a 4-bar mechanism this link 2 is the output, chosen output link. Not always, sometimes link 3 could also be the chosen output link. Another example, this is a 3 degree of freedom parallel robot. It's a spatial parallel robot. It consists of a fixed base, this is called as the base platform, and a moving platform, and this base to moving platform is connected by a rotary joint, a prismatic joint, and a spherical joint. Okay, so in this chain R, P, and S, the P joint is the one which is actuated. So we can again define an axis of this rotary joint and some rotation angle theta 3. Similarly, axis of the rotary joint 2 and an axis theta 2, okay, and theta 1 likewise. And we can also define a fixed coordinate system which is OX, OY, and OZ, okay, at the same, maybe the center of this triangle. And similarly, we can define a point P on the moving platform which is PX, P of X, Y, and Z. Okay, so this has 3 spherical joints on the top. So these spherical joints are not actuated. Okay, so hence we can use multi-degree of freedom joints. In this example, the moving platform typically is the output link. Okay. So in this example, the moving platform is the output link. Okay. And as I said, there are multi-degree of freedom spherical joints which are passive. The original Stewart platform was a 6 degree of freedom parallel robot, okay, and it was invented in 1965 by this person called Stewart, okay, and it consists of a prismatic joint or a sliding joint in each one of these legs. At the 2 ends there is a hook joint and a spherical joint. So this is a UPS arrangement in each leg. There are 6 of these legs, and by sliding the prismatic joint we can make this top platform go up and down, have X and Y Z motion, and also 3 rotary angles, okay, roll, pitch, yaw, for example. This was used to test tires. So basically you mount a tire at the bottom of this top platform, and then you can tilt the tire and you can make the tire go in all the 3 motions, X, Y, and Z, and also the 3 rotations. So it was a tire testing machine. A third example is that of a robot which is a model of a 3-fingered hand. Okay, so we had discussed this once in week 2. So I have a 3-fingered hand. Each finger consists of a rotary joint along the z-axis, theta 1, one more joint along the finger. So these 2 joint axes are perpendicular to each other, and a third which is again parallel to the second joint. Okay, so if you look at your finger, the first one is at the base, the second one is the middle, and the third one is not considered. Okay, so the first joint can both rotate about the z-axis and also rotate about the perpendicular axis, and the second joint is parallel to the second rotation. So the small portion in any finger is not considered in this model. So we have these 3 fingers, okay, so, and the link lengths are L31, L32, and L33. So for the third finger, L11, L12, L13 for the second finger, and L21, sorry, for the first finger, and L21, L22, L23 for the third finger. Okay, these 2 fingers, index and the middle finger are separated by a distance 2d, and similarly from the center of that point of intersection to the thumb is a distance of h. Okay, so you can think of these three fingers grasping an object, and one of the models of grasping an object is this point contact with friction. Okay, point contact with no slip. So if you have these three fingers grasping an object with point contact and no slip, we can show that it can be modeled using a spherical joint. So there is a spherical joint. So this is the object. This triangular piece is the object, and P1, P2, P3 are three spherical joints. Okay, so in this case, the output link is clearly this triangular piece. Okay, so this has 3 degrees of freedom. You can use the Grubler-Kurzbach criteria and show that it is 3 degrees of freedom. However, there are 12 joints. So there are several joints which are passive, which are not actuated. So for example, these 3 spherical joints are not actuated, and we'll see later that only 2 joints in a finger are actuated. Okay. There are many actual applications of parallel robots. So a modern tire testing machine looks like this. So for example, these are the U, P and S, and this is the top platform. The tire is mounted from the top platform, and this is the place which will apply the rubbing or pressure to the tire. We can also have Stewart platforms which are used for micro positioning. Okay, we can also use Stewart platform or 6 parallel robots for robotic surgery and for precise alignment. Okay, so there are several advantages in using parallel robots. One of the main advantages is that the load which the parallel robot can carry is much more. It is basically shared by these 6 legs in this case of a Stewart platform. Another big advantage is that the error in a parallel robot is only the maximum error in each leg. The errors don't add up. Okay, we had discussed this in the first week also. So let's continue. So the degree of freedom of a parallel robot can be obtained using the Grubler-Kurzbach criteria. So DOF is lambda into n minus j minus 1 into sum of all the degrees of freedom at the j joints. So this is similar to the same formula used for serial robots. So n is the total number of links including the base. J is the total number of joints connecting only 2 links. Okay, Fi is the degree of freedom at the ith joint, and lambda is equal to 6 for spatial motion and 3 for planar manipulators and mechanisms. So for the 4-bar mechanism, we can see that n is 4, j is 4. The sum of the degrees of freedom in each joint is 4. There is 4 rotary joints. Lambda is 3. So if you add all these things to this equation, you will get degree of freedom is 1. For the 3 RPS robot, n is 8, j is 9. The sum of the degrees of freedom in each leg is 6 into 1, okay, and then 3 into 3. 6 because there is an R and a P. Okay. So you can think about it. We'll get 6 into 1 plus 3 into 3, and then lambda is 6, so the degree of freedom is 3. For the 3 degree of freedom hand, n is 11, j is 12. The degrees of freedom in each of the joints, okay, so there are 3 spherical joints, which is 9, and then there are 3 rotary joints in each finger, so that is again 9. So lambda is 6, so we get degree of freedom of 6. As I said, in the case of the serial robot, the degree of freedom is basically the number of independent actuators that we can have in this robot or in this mechanism. So in a parallel manipulator, if j is greater than DOF, j minus DOF joints are passive. So example, in the 4-bar mechanism, j was 4, but DOF is 1. So only 1 joint is actuated and 3 are passive. In the 3 RPS manipulator, j was 9, degree of freedom was 3, so 6 joints are passive. Okay. So these passive joints can be multi-degree of freedom joints, as I have mentioned, because we don't need to put actuators to implement a multi-degree of freedom joint. So in the 3RPS manipulator, the 3-degree of freedom spherical joints are passive. In a Stewart platform, the U and the S joints are passive. Okay, so let's continue. So we divide the configuration space, basically the set of all joint variables which completely describe the mechanism or the parallel robot, into theta and phi. So thetas are the actuated joints. Let's say if it is n degree of freedom, there are thetas form an n-dimensional space. Phi is the set of passive joints, and phi could be m of them. Okay, so all passive joints phi, okay, and n plus m is less than or equal to j. Okay, so sometimes we will see later that all the joints need not be passive. They need not appear in this m-dimensional space of passive joints. Okay, so hence n plus m is less than or equal to j. Okay, so the next topic in this lecture is loop closure constraint equation. This is a very important concept, and again we will use the 4-bar example mainly to show the concept of a loop closure constraint equation. So what is the motivation? We have m passive joint variables. So m independent equations are required to solve for the m phi's. Okay, so we can at most give or specify the n actuated variables theta I 1 to n, but we need somehow to evaluate what those values of the m passive joint variables are. Okay, so the general approach is to derive m loop closure constraint equations. And what is the way to derive this m loop closure constraint equation? The standard way is to break the parallel robot into 2 or more serial manipulators. Okay, we determine the DH parameters for the serial chain and obtain position and orientation of the break for each chain. So suppose if I break it at some point, I can put a coordinate system at that place where we have broken, and we can find the position and orientation of that coordinate system. Then we use the join constraints at the break to rejoin or close the parallel manipulator. Okay, so if you want to analyze what happens due to the break, we have to rejoin it somehow in the during the analysis process. So the main trick is to break such that the number of passive variables m is least. Okay, and I will show you some example how we can get different m's depending on how we break the mechanism or parallel robot into serial robots. The minimum number of constraint equation ni of q is equal to 0, I equals 1 through m are to be used. Okay, so this is a standard thing. I don't want to break in a way such that I get many passive variables. Okay, if I can get with a lesser number of passive variables. Okay, as I said, we will look at this 4-bar mechanism many times. So let's see what are the possible constraint equations for the 4-bar example. So 4-bar was link 1, link 2, link 3, and then this fixed link. Okay, so we have one loop which is L, then R, it goes through this loop, and we can go from L to R using this along this translation along the x-axis. Okay, so we fix coordinate systems 1, 2, 3 and tool as shown. So we fix the coordinate system 1 at OL, 2 at the second joint, 3 at the third joint, very similar to a serial robot, 3R planar robot, and then this tool coordinate system is at the end. Okay, so the x-axis is shown for convenience only. So the sequence OL, O1 at the same place, then O2, O3 and O tool basically is a 3R parallel robot. So we are assuming in some sense conceptually that we have broken it at this place. Okay, at this 4th rotary joint. So the DH parameters for a planar 3R robot are well known. We have looked at in the serial robot case, except that we don't have theta 1, theta 2, theta 3. We have theta 1, phi 2, phi 3. Okay, we are using different variable names. So we can see this. What is phi 2? Phi 2 is the angle between the x1 axis and the x2 axis. Exactly same as what we did for the DH parameters for any robot, serial robot. Phi 3 is the angle between the x2 and the x3 axis. This is phi 3. That is the way these angles are drawn in this form. Okay. So we can obtain the DH table. So from this DH table, we can find 0, 3, t. So first row will give 0, 1, second row will give 1, 2, t, and the third row will give 2, 3, t. And then we multiply those three transformation matrices and we obtain 0, 3, t. Okay. So for the planar 3R, the tool of length L3 is given. So we can also find 3 tool t. Okay, and then we can also find tool with respect to the right-handed coordinate system. And if you look at it a little bit carefully, the tool coordinate system and the right coordinate system. So the tool x-axis of the tool coordinate system is like this. The x-axis of the right-handed reference coordinate system is like this. And there is an angle of pi minus phi 1. Okay, so we can find a transformation matrix between tool and the right coordinate system, R coordinate system. Okay, and this is given by minus cos phi 1 minus sin phi 1 cos phi 1, again because of the angle which is pi minus phi 1. Okay, so what is the loop closure equation for the 4 bar? Very straightforward. We go from L to 1, 1 to 2, 2 to 3, 3 to tool, and then tool to R. That should be equal to L to R. Okay, so let's go back and see this drawing once more. What am I talking about? So we have a coordinate system L, a coordinate system 1. So L to 1, then 1 to 2. We have a coordinate system here 2. Then 2 to 3, then 3 to tool, and then tool to R. So this loop, multiplication of all these transformation matrix, must be equal to the transformation matrix between L to R. So directly going from this along the fixed base. Okay, so this is a planar equation. This corresponds to a planar system, planar loop. So although this is a 4 by 4 homogeneous transformation matrix, there are only 3 independent equations in this matrix equation. So, and these 3 independent equations, once you do all this, can be shown to be equal to this: L1 cos theta 1 plus L2 cos theta 1 plus phi 2, L3 theta 1 phi 2 phi 3 is equal to L0. Similarly, the sine component L1 sine theta 1, L2 sine theta 1 plus phi 2, L3 sine theta 1 phi 2 plus phi 3 is 0. Okay, and theta 1 plus phi 2 plus phi 3 plus pi minus phi 1 will be equal to 4 pi. Okay, so let's go back and see the figure once more and see whether it makes sense or not. So I am taking one vector from here to here, from here to here, from here to here. So the x component of the vector will have L1 cos theta 1, then L2 cos theta 1 plus phi 2, and L1 cos theta 1 plus phi 2 plus phi 3 to reach the x component. And the x component should be equal to L0, okay, which is this distance along the x-axis. The y component, I go from here to here, here to here, here to here. The y component will become 0. Okay. The last equation tells you that the angle, okay, the sum of the angles, interior angles of a quadrilateral is given by this formula. So this is a slight difference between the planar 3R and in this case the planar 3R broken at the right joint. Okay, so we will get theta 1 plus phi 2 plus phi 3 and pi minus phi 1 because the sum of the interior angles should be equal to 4 pi. Okay, so In this case, what you can see is we have this loop closure equation contains all four joint variables theta1, phi2, phi3 and phi1. Okay, all the four joint variables are shown here. The actuated joint variable is theta1. Most of the time in a 4-bar, the crank, which is theta1, is the one which is actuated. So we have one actuated joint variable and three passive joint variables. Okay. So in this approach, if I break it at the joint at the r coordinate system at the other end of the 4-bar, I have n equals 1, which is n is the number of actuated joint variables, m is equal to 3, and the total number of joints is 4. So in this case, n plus m is equal to 4. Okay. So let's see what have we done. We have done the DH parameters for one loop. We have obtained the 4x4 transformation matrices, and now we have obtained the constraint equation based on the geometry. In a general or complicated parallel robot, we can also have multi-degree of freedom spherical and hook joint, U joint. Okay, so and more importantly, it is sort of hard to obtain which are the independent loops in the presence of several loops. In the case of a 4-bar, there is exactly one loop. So we can break it there and we show that this is the loop closure equation. So to represent multi-degree of freedom joints, but two or more 1 degree of freedom joint and obtain an equivalent transformation matrix is one way of solving this problem of S or U joint. However, to obtain the independent loops is not easy. Okay, there are no standard ways or not very easy to check which is an independent loop. Okay, so let's consider what happens in a 6 degree of freedom Stewart curve platform. So as I said, there is a fixed base, there is a moving platform, okay, and each of these corner points, so P4, which is connected to B4 by means of a spherical joint and a hook joint and a prismatic joint. Okay, so we have a 6-sided top platform and a 6-sided bottom fixed base, and corner points are attached by U, P and S chain. Okay, so in this case lambda is 6, n is 14, we can count, so 1, 2, 3 and then so on, and you can count that the number of links are 14, the number of joints is 18. Why? There are 6 here, there are 6 here, 12, and then there are 6 prismatic joints, so 18. The sum of degrees of freedom at each one of these joints is 36. So you can see this is 6 into 3, 18, 2 into 6, 12, plus 6 into 1. So this is 36. So if we substitute in the Grubler's formula, we'll get degree of freedom of 6. Okay. So if you have 6 degrees of freedom, we can actuate 6 joints. Okay. And in a Stewart platform, the 6 prismatic joints are actuated. So which means out of this 36 degrees of freedom in the joints, 30 are passive variables and only 6 are actuated. More importantly, we have many loops. So for example, 5 loops are of the form BI, let's say B1, P1, P2, B2 and then back to B1. Okay, so we can start from B1, P1, P2, B2 and then back to B1. Okay, and there are 5 similar ones just by changing I. Okay, then we can have 4 loops of the form B1, P1, P3, B3 and then back to here. Okay, so we can skip the middle one. And then similarly we can have 3 where you skip 2 middle ones and go to the third one after the first and then come back. So we have several possible loops. Okay, and there are 12 of these. Okay, if you think a little bit about it. So each of the 12 loops can have potentially 6 independent equations because this is in 3D space. So the transformation matrices, when we multiply, we'll get a matrix equation, and each transformation matrix has 6 independent equation. Okay, so we can have 12 such loops, and there are potentially 6 independent equations in each loop. So which 30 should we use for the 30 passive variables? So it is not clear. Okay, it is quite complicated. Let's go back and look at the 4-bar example again. So the first time I showed you, we broke at the OR, the last link. We could also break at the joint 3. So if I break at joint 3, then I have a planar 2 degree of freedom and a planar single 1R robot. So 2R and 1R. I could have also broken it in the coupler link. So at a distance A and B, somewhere here I can break it at link 2, sorry. So then what do we have? We have two planar 2R robots. So 1R, 1R and some end effector point. Similarly 1R, 1R and then another point here. We can also break at 2 places. So we can break at the second joint and third joint. So these are possible ways of breaking this 4-bar example. And let's try to find out the loop closure equations, the relevant equations for each of these 3 cases. So first is we break the loop at the third joint, which is case 1. So I have a planar 2R manipulator and one planar 1R manipulator. So we can again obtain the DH table for both. It's very easy to obtain L to 1, 1 to 2 and R to 1. Using L2 and L3, we obtain L tool transformation matrix and R tool transformation matrix. So from L tool, extract X and Y components of this point. Okay, so we can extract the X and Y component of this point here. Okay, so what will it be? It will be similar to L1 cos theta 1 plus L2 cos theta 1 plus phi 2. So the X component of this point will be equal to L0 plus L3 cos phi 1. Okay, that is what I am trying to get at. Okay, so that is what is there. So X component from the left side is this, Y component from the left side is this, and from the R coordinate system, the same point is L3 cos phi, L3 sin phi. So now we can write the loop closure equation, which is L1 cos theta 1 plus L2 cos theta 1 plus phi 2 is equal to L0 plus L3, because we have to move along the X axis by L3. And if you equate the Y, okay, we have L1 sin theta 1 plus L2 theta 1 plus phi 2 is equal to L3 sin phi 1. Okay, so what have we used here? We have basically used the constraint for an R joint. So recall in week T2, we had looked at what are the constraints imposed by a R joint. So we are at the point, okay, where we have broken. So at this point, basically the XY position coming from this side should be equal to the XY position coming from this side. Okay, we don't have to worry about the orientation. Remember, a rotary joint imposed 3 position constraints. In this case, since it is plane, 2 position constraint, and we also had orientation, but that is not useful here. Okay, so we have Q, in this case theta 1 phi 1 phi 2. So you can see the equations do not contain the rotation at the joint where we have broken. Okay, so theta 1 is actuated, so n is 1, and there are 2 passive joints phi 1 and phi 2. So n is here n plus m and j is 3. Okay, so as I said, we can also break the second link, the coupler link, and we get 2 planar 2R robot. Again, we can obtain the X and Y components of the point where we are breaking from the left side and also from the right side. Okay, so from the left side, it is L1 cos theta 1 plus A into cos theta 1 plus phi 2, and Y is equal to L1 sin theta 1 plus A into sin theta 1 plus phi 2. Okay, likewise, from the right side, we can write the X and Y components in terms of angle phi 1 and B and phi 3. Okay, here A comes because you have broken at distance A and B. And we can impose the constraint that the broken link is actually rigid. So what is the constraint when you have a rigid link? The positions are same and the orientations are the same from both sides. Okay, so x from left side will be equal to right side, y from left side will be equal to y from the right side, and the orientation of the coordinate system where we have broken is given by theta1 plus phi 2, and from the other side it is phi 1 plus phi 3 plus pi. Okay, this pi comes because the x-axis is pointed opposite in the two coordinate systems. So in this case, we have similar to the case when we broke it at the third joint. So we have n is 1, m is 3, and j is 4. Why? Because we have theta 1, phi 2, phi 1, phi 3. So all the joint angles appear in these three constraint equations. Finally, we can break it at the end of the first link and end of the last link. Okay, so we can obtain the points L from the left side, which is nothing but L1 cos theta 1, and this is L1 sin theta 1. And from the right side, we have L3 cos phi 1 and L3 sin phi 1. Okay, so what is the constraint we want to enforce? We want to enforce that the link length 2 is always constant. Okay, so the link 2 has link length 2. So basically the constraint is x from this x minus this x square plus this y minus this y square is equal to L2 square, which is what is written here. So L1 cos theta 1 minus L0 minus L3 cos phi 1 square whole square plus L1 sin theta 1 minus L3 sin phi 1 square is equal to L2 square, or minus L2 square equal to 0. Okay, so this is very similar to the constraint SS pair introduces, okay, in a loop. So in a plane, the SS joint, SS pair is similar to a RR pair. So what do we have here? Here we have only one constraint equation with one theta 1 variable and one phi 1 variable. So Q contains theta 1 and phi 1, so n and m equal to 1, and j is 4 here. We still have 4 joints in the mechanism. So this is a very well-known equation. This is called as the Freudenstein equation. Okay, so if you look at 4-bar kinematics and if you go and search for Freudenstein equation, so in 1954 he derived this equation for a 4-bar mechanism. More importantly, he went on to use this equation to design 4-bar mechanisms. So lots of possibilities of using this equation to design a 4-bar for 1 position, 2 position, and 3 or 4 specified positions are possible. Okay. So as I said, we have 2 problems in kinematics of parallel robots. One is the direct kinematics problem. It's a 2-part problem in this case as opposed to serial robot. First, step 1, given the geometry of the manipulator and the actuated joint variables, obtain the passive joint variable. Okay. So for example, in this equation, if you are given theta 1, we can use this equation theta 1 comma phi 1 equal to 0 to obtain phi 1 somehow. Okay, one equation, one unknown. So now, but we need to do some more work to obtain the other 2 passive joint variables. Nevertheless, we can obtain all the passive joint variables. Second step is, once you obtain the position and orientation of the chosen link, you need to obtain that. So once you obtain the active and passive joint variables, we can go back and substitute in the general equations of a 4-bar mechanism, okay, without breaking. So every variable is there, and we can find the position and orientation of a chosen output link. Okay, so this is a much harder than the direct kinematics for a serial robot, because why? It is 2 steps. In the direct kinematics of a serial robot, just the actuated joint variables are given and we find the position and orientation of the end effector. That is not enough. first you have to find the passive joint variables using the loop closure constraint equation, and then obtain the position and orientation of the chosen output link. The solution of the direct kinematics problems, specifically the step 1, gives rise to something called the notion of mobility and assemblability of a parallel robot or a closed loop mechanism. So we will see later that when you try to obtain the passive joint variables, we'll obtain conditions, okay, that some of the passive joint variables do not have real values. Okay, so that leads to this notion of mobility and whether you can assemble the parallel robot. The inverse kinematics problem is different again. So what are we given? They're given the geometry of the manipulator and the position and orientation of the chosen end effector or the output link. Okay, so depending on which is the chosen output link, the inverse kinematics problem will be slightly different. Okay, so if I choose the fourth link in a 4-bar mechanism as the output link, the inverse kinematics is different than if I choose the coupler link. So first we have to obtain the actuated and passive joint variables. Okay, and that is the problem once you choose the output link. This is simpler than the direct kinematics problem, we will see later. Okay, it is also normally simpler than the inverse kinematics of serial robots. Okay, and this could be often done in parallel. Okay, so depending, and we will discuss this notion of doing it in parallel. Okay, and this is one of the origin of the term parallel in parallel robots. Okay, why? Because we can solve the inverse kinematics problem using parallel computation or in parallel. So in summary, parallel manipulators have one or more loops and no natural choice of end effector. Okay, you have to say this is my end effector, and you have to say which are the loops we are, there are more than one loop. Parallel manipulators, the number of actuated joints is less than the total number of joints. Hence, there are some joints which are actuated and some joints which are passive. Okay. The degree of freedom is less than the total number of joints. This is also very important. In a serial robot with 1 degree of freedom joint, in a Puma, we had 6 rotary joints and the degree of freedom was 6. In a planar 3R robot, we had 1 degree of rotary joints, 1 degree of freedom rotary joints, and the degree of freedom of the planar 3R was 3. Whereas in a parallel robot, the number of joints is much more than the degree of freedom. So this leads us to this notion of a configuration space of a parallel manipulator. Basically, we call this configuration space Q. It is divided into 2 parts. One is theta and one is phi. Okay, so thetas are the actuated joints and phi's are the passive joints. So, and we would like to choose the dimension of Q as small as possible. So thetas are fixed. If you have 3 degrees of freedom parallel robot, the dimension of theta will be 3. But we could arrive at different phi's as I showed you for the 4-bar mechanism. Okay, so we could have just 1 phi for the 4-bar and 1 actuated, or we could have 1 actuated and 2 passive, or you can have 1 actuated and 3 passive joints. So we would like to choose the dimension of Q as small as possible. Okay, so there are typically n degrees of freedom in a parallel robot, then theta will be n dimensional, and if you have passive variables, they form a m dimensional space. So we need to derive m constraint equation. So here phi should be element of Rm. Okay, so in order to solve these passive variables, we must have m constraint equations. Okay, and as I said, there are 2 problems. One is direct kinematics and one is inverse kinematics of parallel robots. Okay, so with this we will stop, and in the next lecture we'll look at direct kinematics of parallel manipulators.